Please, welcome back to the stage, co-founder and CEO, Anyscale, Robert Nishihar.
Thanks for an amazing day one of Race Summit. We've got a lot of amazing user presentations lined up for this morning. I hope you had a chance to check out some of the talks yesterday and learn something new. But let's get started with an update on generative AI at Adobe from Urson Umer, Senior Director of ML and AI Platform at Adobe. Please welcome Urson.
Thanks, everyone. Super great to be here. I'm super excited to talk about generative AI at Adobe and what we do with Ray as well. So I was reminded that it's going to be very early for my talk, so I have included quite a bit of eye candy to hopefully wake you up. Also cover the fact that I have not really worked on my talk track, so bear with me as I look at the slides, try to look back at you. But we launched a lot of these generative AI features that actually started with a decade-long research at Adobe that folded into a playground of text-to-image generation and quickly folded into many of the Adobe products. And I want to really give you a quick view of what our users are able to do with it today.
Future looks like wow. Oh wow. It's like wow. Yeah. Future looks like wow. Oh wow. And it starts right now. Yeah. Future looks like wow. Go and get it, go and get it, go and get it, go. Go and get it, go and get it, go and get it, go. Go and get it, go and get it, go and get it, go. Coming up right now, and it's looking like how? Wow. Wow. The future looks like wow, and it starts right now. It's like wow, introduce, yeah. It's a brand new future. Wow.
Thank you. I was told by our marketing team this is the best spot to get off the stage, but I'm not going to listen to them and try to talk over a few more slides. So Adobe Firefly, as I mentioned, started as a research and a playground with a text-to-image model that was launched on a beta website in March 2023. And as Gen AI has been moving really crazy this year, our users so far have generated in the last 6 months over 2 billion images with it. Adobe's Firefly and image generation through text is really extremely differentiated from other offerings in the market, specifically because it's commercially available, right? To the extent that we are actually indemnifying our enterprise users because we believe we are using data responsibly and only using data in our models that are commercially available and viable. And we also have offerings where these enterprise customers can train their own models using our foundational model too. So we not only use our own foundational model and commercially viable data for the general public and enterprise users, for those specific users and enterprises that are interested in training their own models with their own branding and own data, that's also going to be available very soon. As Gen AI has been moving and accelerating throughout the past year, Adobe has been also on top of the speed, and not only we launched the Firefly beta back in March, we quickly folded into Photoshop, as well as Illustrator and Adobe Express. We also announced with Google that Firefly will be served inside of Google Bard. And very recently, we have started with talking to our enterprise customers about the train your own model concept, which is also very interesting. The three areas and creative products that Adobe has and has been serving the creative community for tens of years now, Photoshop, Illustrator, and Express, all in one creative product, have also been benefiting from Firefly, right? Photoshop has generative fill now, expand image. Illustrator has generative illustration, coloring, and design. And Express has all these features folded into creating really flyers, marketing products, and beyond with the generative features that we have provided with the Firefly service. So specifically in the GA that we launched with Firefly, you're now able to go in online and be able to generate images that you can use commercially. We do have content authentication with our images generated on the platform, so you can actually track back and see where that content was generated. Does it include generative AI, which is really going to be an important thing going into the future, to be able to see, understand, and validate where content comes from. On the Photoshop, Illustrator, and Express side, we are really trying to create the future of creativity, right? Back in the day, and I'm going to show a few examples of this soon, back in the day with Photoshop, when you wanted to edit your image and make it more professional or erase somebody from the image, this would take hours or maybe really someone professional help. Whereas today, you can do some of these simple operations really fast with the help of generative AI. And this not only increases the availability of these tools to the general public, but also increases the speed and productivity of our creative professionals as well. So one of the features I really, really like is not only expanding an image, but also doing very simple selection and then basically changing a piece of, a semantically meaningful piece of an image, right? It's really easy to get production shots like this and then work on those hours for creative professionals to turn them into something like this. Before Firefly and generative AI and Adobe tools, today this becomes a very simple interaction with the generative fill tool. Next, I will talk about a few things about data and why they are important, but also I'll introduce where we use Ray in our platforms. Some of these things that Ray enable us do are my favorite things as well. But from experience, data has been always the most important thing for AI, and this hasn't changed with generative AI as well. I have often actually seen researchers dabble into trying to do architecture changes and improve performance or boost a specific part of the inference model in either LLMs or image generation or any other area of AI. But really, what you can incrementally get from making those changes in your training code or the way your architecture has different layers or different number of filters in your layers, rather than optimizing those, I often advise people to look at their data almost 90% of the time and try to curate a lot better data for training rather than working on model architecture, for instance, itself. Of course, there are big jumps that will come from model architecture like we got from convolutional neural networks in processing images, but most of the time, data becomes really a big part of it. And we have actually started seeing this in LLMs as well, right? large-scale scraped data that trains an LLM for millions of hours can be often beaten or maybe got really close to with a very specifically curated, only maybe to the extent of 100,000 or so specific examples. We do take a very similar approach, and we curate our data constantly at Adobe as well. So our data platforms are actually part of a larger platform that we build and abstract with Ray itself. We do work on the cloud, so anything that goes into representing our compute and storage is going to be compute in the cloud and storage in the cloud. We do provisioning on top of this, either specific to the cloud provider, or we mostly also use Kubernetes. And as you know, Ray is also natively able to be launched on a Kubernetes cluster as well. A lot of this tooling and low-level work that we do on provisioning, introducing infrastructure tools, health monitoring, observability, is really abstracted out from the user and has to be abstracted out from the user for being able to get a lot more performance as well as productivity throughout these tools. So we have 3 different pillars in our platform. One of these pillars is the interactive boxes. This is often where researchers would be developing and trying out ideas before actually launching a batch job. The second pillar is a multi-tenant scheduler. This is A100s. We are switching to and adding more H100s here as well. This is where multiple users use an interface and CLI to actually launch a lot of jobs with a lot of GPU and compute needs as well. The third one is specific to data and where we mostly use Ray to tap into heterogeneous compute as well. Because when we're doing offline data processing, we really don't need the high-end expensive GPUs for inference, even though we use 10 to 15 models depending on the specific processing needs of data before even like training on that data. We use 10 to 15 models, deep learning models to do various operations, data augmentation. This includes cleaning up, this includes enriching metadata, this includes NLP metadata enrichment methods as well on the text pieces of the captions and the text. But really that data pipeline is super extensible, and with Ray, it's extremely efficient and quick to add offline new models to do inference on and then quickly tie them up to the data processing pipeline. There are a few things we like about Ray. One of them is the fact that it's very flexible and we can use it for our interactive sessions, for our batch job sessions. It's extensible, and one of the features I love myself is being able to add, as I mentioned, these inference models really quickly to production, right? We can reuse the inference models also for batch processing as well. That's when we can quickly launch data jobs that basically span tens of thousands of CPUs and heterogeneous compute with GPUs as well. It is also very scalable. We do have everything in Python. The rest of our stack, most of our AI stack is in Python in the offline case for training and for data processing. So it really fits in nicely. It also fits in our users' experience of using the large cluster with our framework for scheduled jobs. We are also evaluating RayServe on the real-time inference side. And this is one of the areas that I'm also excited as well. I've seen multiple of the talks where others have been tapping into the power that's provided by RayServe and the extensibility provided by it. So I'm looking forward to deepening our Ray use and going into RayServe potentially at some point in the future as well. So with that, before handing off the stage, I want to talk about one more thing on the data side. In the generative AI space, we have been seeing all of this basically scraped and used data for various different models, various different applications, right? The extent of that and not really responsibly using that data is on one end of the problem. The second end of the problem is when content is now generated with these LLMs or with these image generative models, how do you verify where that content originated from and where did that start? And when you look at an image, is it real? Has it been modified with AI? So all these questions are going to be important questions to answer. So this is why I want to kind of pull your attention to the content authenticity initiative that we are collaborating with Microsoft, NVIDIA, and a few others, where we have now committed to anything you have generated with Firefly will have an embedded information about when and how it was generated and whether it was modified with AI or not. And we are hoping the adoption will be larger and larger into the future because it's really important to use data responsibly and reuse it responsibly as well. And with that, thank you so much. Hopefully I didn't go off track too much.
Please, welcome to the stage, from Uber, Vice President of Engineering, Albert Greenberg, and Engineering Manager, Wei Kong.
Hey, welcome. How many devs are in the audience? We got, awesome. So this is going to be a dev-oriented talk. Standing next to me is Wei, who's in our dev productivity group. And later today, we'll have the talk from Zitao, who's in the Michelangelo or AI group. So really what's going to happen in this talk is we're going to talk about a mixture of the, let's say, the AI stuff and the dev productivity stuff. And I think that's exciting and it really works. So, if you're going to remember 4 things about this talk, I think 1, Uber uses AI, has done so since 2015. We're a big and heavy user of AI methods. 2nd, Uber uses Ray, an early adopter of Ray, and we're happy to adopt it and continue to use it. 3rd, Uber uses generative AI, and that's working out for us. And 4th, Uber uses generative AI to improve developer productivity, which is really one of the ways we're improving productivity across the company. Those are the 4 things that I'd like you to remember. Let me move on. Okay, so Uber by the numbers. Uber serves more than 70 countries. Uber, serves about 25 million trips a day. We serve 10,000 cities. And we have about 137 million monthly active users. And the financials are working out. That's what the up and to the right arrow suggests. And you can see that we were GAAP, generally accepted accounting principles, profitable in Q2. And that was really good. We have these 3 major lines of business, which you might know as rides, eats, or grocery, and freight. So Uber AI by the numbers. We have about 5,000 models in production. We have about 10 million operations at peak running. So while I'm speaking, millions and millions of AI operations are running, predictions of all kinds. And you see the phones here. And really these are views of the phone for different users of our application. So there's on the left, the earners, the folks that are really doing the hard work of driving and delivering. And so what this shows is how they, get their documents uploaded, comprehended, and get going in a very easy way using machine learning methods. Second, the riders, if you use the app, then you'll see that the app will suggest, based on you and the time of day and various factors, where you likely are going to want to go to right away without, it's going to suggest I go back to my hotel when I get out of this stage. So and then finally, the EAT. So the machine learning methods will propose to you good choices that you tend to like, and for groceries as well as food to eat now. So here's in a glimpse the sort of Uber journey on machine learning methods. We started again around developing this stuff in 2015, and really it went live in 2016. And you might have heard of the Michelangelo platform. The dashed lines just show the rate of adoption of the Michelangelo platform, which is our platform for delivering AI the same way we deliver code with CI/CD, continuous integration, continuous delivery. And that's been a huge uplift for our developers and as our data scientists as well. And I'll talk a little bit about that. So we have always been a major consumer and contributor of open source. So you'll see some open source names, including the Ray name and Horavat and other names as we progressed in our journey. And we use the same kind of coolness in GPUs and so forth that Ursum talked about. So around 2023, you start to see this dashed orange line jump up. That's the generative AI, which is really what has got us all excited and why the audience is filling up. So, the reason we're able to iterate quickly is this platform called Michelangelo. And it supports all elements from ideation to extracting the data, creating the features, training, evaluating models, and then deploying, monitoring, all the way down to decomming of the model. And the models are kept fresh. The users of the models are given continuous feedback based on this platform. So it's part of the life of Uber is to run on Michelangelo. And so really what you see here is a slide with those orange, blue, and green boxes overlaid on the actual Michelangelo API here. And so it says Michelangelo Studio. And then there's different, it's the real thing. So like a token has a little asterisk by it. That's a reminder to the user they have to re-authenticate. This is what a regular user would see every morning or whenever they work to come and use their models. And it covers, again, the stuff on the bottom, preparing and analyzing data, training and evaluating, deploying and predict, experiment and productionalize, monitor and debug. And the idea is to get through this pipeline with super reliability so that they can iterate the users and improve and take feedback and then go fast. So one of the models that we're proud of is called Deep ETA. ETA is expected time of arrival. Expected time of arrival is very central to the Uber experience, what we call the magical user experience. So we've done lots of iterations on this model. And we're also a very open company, so we wrote about it, we blogged about it. So you can look up Deep ETA, deep for deep learning, right? So this is a model that it's one unified model that covers all the different applications. We could have done 10 different models and then let's say, only train one on one set of data, but we really wanted to go after training one powerful model and using it in many, many scenarios, and that's worked out for us well. So the model has about 100 million or so parameters, and it's trained over billions of trips. So that's what gives the ETA the smarts that it has to predict based on all the different conditions in real time what the ETA will be. And the math is a lot more complicated than that little equation at the bottom. So when we look at generative AI, and Ursum touched on this a little bit when he talked about productivity, really we see it democratizing and helping pretty much everybody in the company. And it's just incredible. We said, well, let's focus on 3 things, but everybody wanted to use it. And there's so much creativity, and it's quite easy to get started with generative AI. So we see applications to devs, the SWEs, the data scientists, the data engineers, the machine learning experts, the program managers, the technical product managers, operations, the folks that actually, work the cities and make sure that everybody has what they need, and marketing and legal, creating, summarizing, discovering, and automating all these tasks. And below is, the Michelangelo platform, which I'll talk a little bit more about, and just the tons of different inputs and systems that we combine to make it all come together under Michelangelo. So at this point, I'm going to hand it off to Wei, who will talk a little bit with you about how we use these generative AI models to improve developer productivity.
Thank you, Albert. Hello, everyone. My name is Wei. I'm an engineer manager from Uber. I'm excited to discuss some of our AI-powered projects we're working on to improve developer productivity. First of all, who doesn't want more free testing? We are leveraging AI to improve testing efficiency. This video shows our AI performing virtual trips in the rider and the driver apps in New York, San Francisco, and Paris. We are building a large language model, Dragon Crawl, to simulate trips for any city and language. These combinations are impossible to test manually and difficult to automate. If you look closely, there are differences in each trip that our AI can handle reliably. We believe this will significantly improve quality for our customers, higher quality with less effort. We plan to have a Dragon Crawl perform automatic mobile end-to-end testing in all cities, languages, and all Uber products in the near future. We can't wait for Dragon Crawl to be delivered. It will be a game changer for mobile testing. Next, let's talk about code assistant. We have integrated with an external code assistant, but are seeing different results. Our developers generally like it, are happy with it, indicate that it is very useful to write 1 or 2 lines of straightforward and repetitive code. The biggest downside is that up to 2/3 of the code suggestions require further editing. Either they won't compile or they're not quite right. This is because the external code assistant cannot train on our Uber code base. It can only train on publicly available code. To close the gap, we are supplementing it with our internal project called Uber Code Assistant. We're building a large language model that incrementally pre-trains OSS models on the Uber code base, supporting all languages used at Uber. The OSS models we're using are CoLlama and StarCoder. Once we integrate this internal model with our IDEs, VS Code, IntelliJ, and Xcode, we will be able to provide our developers much more accurate, relevant suggestions tailored to our code base. With that, I will hand it back to Albert. Thank you.
Thanks, Wei. It may be hard to understand, but testing mobile apps is incredibly difficult. You have to be okay in every language, every form factor, every release of the OS. And what we find is these generative AI models are just robust to all those little things. So there's just a combinatorial explosion of things you want to test. It's very hard to do it with people, but the model, the Dragon Crawl model that Wei described manages that way better than we've ever seen before. So we're super excited about that. One of the things that I think you've heard in this conference is that there's kind of horses for courses. There's different, machine learning models with different trade-offs, like you see in this graph, that depending on what you're doing, you want to pick the right model. You want to have the right kind of catalog of models. And, the models that Wei just talked about are the like Code Llama and StarCoder are small ones that we can prompt engineer, fine tune very easily, and it's in our hands and change, and they can be used, for example, to give, we can trade off to get better accuracy as by, the technique in this paper, distilling step by step, or we can, use task-specific models and get, really good results with more training data. So what we've found, let's say that, what are the order of priorities for us? And really it goes to trustworthiness at the end of the day. So one is privacy. We're super concerned about protecting the privacy of all the parties involved. That's number one. After that, the accuracy. It must be accurate for these testing and coding things. For example, it is an assistant, but if it's not accurate, then developers will not use it. If it's only right, say 2/3 of the time, 2/3 is pretty amazing. But with the enhancements with our own data, we do much better. The latency is very important. The time to market is kind of amazing. It's so fast to at least get a prototype done and then start to harden. And then cost optimization. That's the order of priority for us. So what is our strategy? We have, at the top of this diagram, the different models that we use. So we can use the world or generalist models from the hyperscalers, and we do. It's fantastic for the conversational chat and the simplicity. The accuracy is good. Latency is okay. And then we consume the open source models as well. And we're very happy about that. And that little blender symbol in the middle is there for a reason. We blend these models, and we allow the developers to have a choice of models and blend the results. Then I don't think you'll get the kind of accuracy, and I think Urson mentioned this too, without using your own data, training on your own code, and training on your own proprietary data, which we do. And we get all that done and kept fresh and accurate and timely and all that goodness and private through the Michelangelo platform. And that platform builds in gateways and such to ensure the compliance, the privacy, and the accuracy. So it won't see the light of day to these different communities without all those things assured. So here's the new Michelangelo. That has been enhanced to support generative AI. And the enhancements are in the orange boxes. So we have a catalog, I mentioned. There are lots of different models out there. And we want to, let's say, not early bind what is the right model. We want to give developers a choice and let them try things and replace things as they go. So there is a new module in Michelangelo for prompt engineering, which is a big part of what we do. It's just really so amazing to see this stuff. Like, for example, the observability team prompted in our own Uber internal version of SQL, and it speaks our own internal version of SQL, and is able to help, in production settings where it can't learn this stuff from GitHub. And then there's all the goodness that we've already done at Microsoft, that's Freudian slip. I used to be at Microsoft, at Uber on Michelangelo. So it's the preparing the data, the training and evaluating, deploying and predicting, and monitoring and debugging. All that stuff has to just work. It has to be super reliable. And then developers will trust it and make it part of their daily life. So what are a few takeaways from the talk? We are a big AI-first company. We've been there doing that for years. Michelangelo got started in 2015, and we continue to bet big on AI. The thing that I highlighted here is for real, that we believe and we are investing to improve productivity and the user experience. For example, the DPTA improves the user experience. What we've observed which is really exciting, is the democratization of this stuff. That so many communities, I mean, like the fintech teams, are just quickly producing amazing AI, speaking in their language, using generative AI. And we'll continue to evolve that and make it safe using the Michelangelo platform. What about the generalist large language models? They're powerful, but they're not good enough. They'll get you, let's say, 2/3 of the way there, but not to where you need to go. And so for that, you'll need to customize and combine, blend the generalist models with your own custom models. Then you can get to where you need to be. And when we did that, we found in this order, we had to consider privacy, security, accuracy, latency, time to market, and cost. That's it. I'll be around if there are any questions.
Please, welcome back to the stage, Executive Chairman Anyscale, Professor at UC Berkeley, Jan Stojka.
Thank you and good morning. So we are living not only in the golden age of AI, we are living in the golden age of hardware accelerators. And this is driven by three developments. The first, it's a growing demand. Again, this is a plot showing the growth of the demand in the compute to train the largest models since 2010 versus the Moore's law. So computation demands to train this model have grown 10 times every 18 months, while Moore's law is only growing 2 times every 18 months. And as you know, Moore's law for the past decade has been slowing down, so the gap between the demands of these models and capabilities of a single node or a single processor are even bigger than this plot suggests. This is from last year, so if you add what happened since then, things didn't change much. Here is GPT-4, so you can see the growth in the demand of these models has grown unabated. Now, how do you bridge this gap? There are 2 ways to bridge this gap. The first, build hardware accelerators, which has specialized architectures for AI workloads. Through innovation in the architectures, you can do much better than general purpose processors. And obviously, the second one is distributing these workloads over more and more machines. This huge growth also has big impact on the cost. Again, here is a cost to train GPT-3, which was released in 2020. It was between 4.6 and 12 millions, depending on the source you are looking at. And 2 years later, GPT-4 was released, and it cost over 100 million to train, according to Sam Altman, the OpenAI CEO. And you can see this is a huge gap between 8 and 22x, depending what numbers you are going to use for GPT-3. But things are even more challenging, because you may have the money to train, but you may not find the GPUs to do so. GPU shortage was one of the big stories for the past year. It still is today. And this GPU shortage was so severe that it impacted the roadmaps even of a GPU-rich organization like OpenAI. So not surprisingly, these trends, very fast growth, very high cost, and severe scarcity, creates actually a big opportunity in the market for hardware vendors. So not surprisingly, during the past year, you have here announcements, or you've seen the introductions of new hardware accelerators. And Ray developers want access to these hardwares. They want because they want to have the ability to match their workloads to the best hardware to improve availability, improve performance, reduce the costs. And Ray gives you that, in principle, that ability because we build Ray from day one for heterogeneous distributed computing. That's what we build it for. However, for a long time, Ray used NVIDIA GPUs and then started to use the TPUs. It's also down to the academic roots. But with these new developments and new hardware being released, right now we are putting a renewed emphasis on supporting these new hardware accelerators. So this is what this keynote is about. So in this rest of the keynote, you are going to hear from some of the vendors of these new hardware accelerators, from AWS, which develops Trainium and Inferentia, from Intel, and then from Google TPUs about the latest developments. So first, AWS. As you know, AWS is the largest cloud, and many of us have started our cloud journey with AWS. Recently, they introduced their own AI accelerators, Trainium and Inferentia. And next, please join me to welcome Richard Heaton, the director of Neuron Software at Amazon, to share with us the developments in adding support for Trainium and Inferentia to Ray.
Hi there. Thanks, Jan. So as Jan said, my name is Rich, and I am responsible for the Neuron software stack, which is the software that couples with the Trainium and Inferentia chipset that we build at AWS. So when you think about the chips that we're building, it actually was helpful. I heard Jan's talk about Moore's Law, and actually Moore's Law itself has some interesting ability to predict how chips have been built over the last 50 years, but it eventually started to tail off. As we started looking at that and thinking about the machine learning workloads, they are far outstripping the pace of that growth. I mean, if you look just simply in the last 6 years or more since 2018, we've seen a growth of more of 3,000 with respect to the parameter size of the models that we're training these days. And so that lends itself to finding new solutions and things that we can address the costs that we just talked about and that Jan mentioned, and finding ways to build unique chipsets that can address that in new ways. The good news about ML is that it's highly parallelizable, meaning that you can exploit that and find new chip architectures to address the needs for that workload and yet do it in a parallelizable way. So then as we looked at this, we realized that we could build these purpose-built chips and be much more highly efficient in the way in which we could address them. So we started building that and actually released our first product back in 2020, which was the Inferentia 1, or Inf1, and the Inferentia chip, which we saw great results. Our developers and our customers were able to see 70% improvements in terms of the cost of running those inferences, particularly at scale. And so we continued that journey, and last year we released our next generation device, the Trainium and the Tier N1 server, which brings with it some significant benefits in terms of, again, cost reductions, time to train. We followed that again then earlier this year with the Inf1, Inf2, and Inferentia 2 platforms that provide, again, the optimized inference that, again, helps with the inference workloads. And so when you see the abilities to reduce those costs, improve your times to train, it means you've got more time to innovate, more time to iterate, and you can actually build these amazing kinds of generative AI solutions that we're all seeing these days. I mean, I'm amazed to see all these things coming out. It's amazing to see chat services and assistants and image generation and everything else that's being done. It's just a truly amazing kind of explosion of these activities. So we're happy to be part of that, happy to offer some solutions that are really going to help with some of those areas of growth. And so when you look at the results that we're seeing, Trainium is certainly seeing 50%. Some of these large language models that are really stretching the boundaries of some of this infrastructure. We're seeing great results of being able to reduce those costs, reduce those times to train by 50%. And similarly on the inference side, we're reducing those costs by 40%, price performance ratios especially. And so the interesting thing about the Inf2 as well is that it's the first instance that we've built at EC2 and Amazon that is actually an inference optimized server with an ability to scale out, to handle that scale out form of large language model inference because of the inter-chip connects between these chips inside the server. That gives you the ability to handle these massive large workloads in an inference optimized server. So to make use of these, we do, of course, have to supply a lot of software. It's a very complicated area. And so we build a software stack called the Neuron SDK, which provides a compiler and a runtime stack and a variety of other tools. And then we integrate that within frameworks that we all make use of, like PyTorch and the other libraries that come along with it. And so when you start to look at that, you realize that those software integrations are really the key to being able to make this whole system work well. And so we continue to work towards making it easier and easier to build these solutions, to focus on building your models and training them and deploying them, and a little less on focusing on the infrastructure and those other kinds of areas of work. So I'm very happy to announce that as of 2.7, Ray now does support the Trainium and inferentia-based platforms that we supply at EC2. And that allows you to get the benefits of Ray, ease of use. It can define your clusters, it can define your actors and tasks, and it can really make your life easier as you want to build and deploy these kind of large-scale models. Train and Scale both are now supported. I think Train came out as I probably typed that. So I think as it stands now, this is a great integration. We're really happy to see it. Many thanks.
Intel requires no introductions. Everyone at some point in their life, I'm sure, used computers with Intel chips. Intel provides the most diverse portfolio of chips from CPU to GPUs and everything in between. Please join me to welcome Arun Subramanian, Vice President of Cloud and AI at Intel, Execution and Strategy.
Thank you, Jan. Great to be here. Love to see all the energy around generative AI, and I think I have to drop the mic now after that introduction, saying there's no introduction required for Intel. But just in terms of our overall portfolio of products, not just for generative AI, but the overall portfolio, starting from the CPUs all the way up to the largest clusters possible. Whether you're starting to build out small models, you're experimenting with it, before you go off to accelerators to scale them, to starting to build out just individual servers, and then go off to building medium-sized models to large-scale models, we actually have prepackaged solutions that we work with our partners, with our customers, to scale across the board. You may not have heard the term megapods out there that widely, but really what a megapod is the first, I would say, a graduation after a server where a group of data scientists or a team wants to go off and scale in a small environment that's completely self-contained. Think of a megapod as, in this particular instance, 8 accelerators working together in sync with all the networking, all the high-speed storage you require to not only train, but also do distributed inference at scale. And the greatness of the megapod is once things start working in a megapod, you've graduated from a server to running across multiple servers, it's actually scaling all the way up to an entire data center scale workload that will work across in the same code base, right? And we've scaled this significantly and working first and foremost internally for ourselves to make sure that these things work at scale. So what we call the internal AI supercomputers have actually built data center class models. So the first model that was published was what we call the Bridge Tower model that was built in collaboration with Microsoft Research. It recently actually broke a few records. If you look at the fine-tuning performance of that particular model, it's more than 2 times faster than A100 on any given day. And the latest updates that Hugging Face did, this is not Intel telling you that our chipsets are great, our systems are great. This is actually results published by Hugging Face. It's actually 1.4 times faster out of the box. No optimizations required on either side. Right? So it's apples to apples comparison. You can go do this today. Out of the box performance comparison of what you find on our code on GitHub versus what you find on, say, the H100 code base. Right? That's on fine tuning. The latest results as of a week and a half ago from MLPerf is on the top right, that you see where on the inference performance on GPTJ, again, across the board, like we are more than 2x faster than A100, the 80 gig version of A100, right? Not the smaller one. And we're coming pretty close to H100s. And it was awesome what Ian mentioned about even if you had the money, you would be hard pressed to actually find accelerators out in the market today. This is raw performance. If you do price performance comparisons, we are easily 2 to 3 times better than any accelerator out there in the market today, right? And again, Hugging Face agrees with us. You go look at all of these models running out of the box with Hugging Face transformers, the same results on performance as well, right? Now, if you look at across the board, we've been a great partner with Ray. Ray runs natively, of course, on all Xeon platforms. Any of the pipelines that you're looking at, whether you're training, you're fine-tuning, or you're deploying your models either in your data center, your edge inference, or in your client, we actually work very closely with Ray on deploying it on the x86 systems. I'm super glad to announce that the native Ray support for Gaudi 2s are coming very shortly, before the end of this year, and that will be natively supported across all our Gaudi 2 systems as well. Okay, and this is super important, especially going into the heterogeneous infrastructure required to go scale generative AI of all sizes and all scales, right? So when you're starting to deploy, when you're starting to train, and you're starting to fine tune, and then go off and deploy into the real world, it's really the ability to go do that quickly and efficiently as you cut across your heterogeneous infrastructure. And this is hot off the press. Just a couple of minutes ago, our CEO announced this partnership in our conference going on in San Jose. Glad to announce that we just had a major design win with one of the largest AI supercomputers that's going to come live later this year. It's thousands of accelerators, Gaudi 2-based accelerators, and Xeon processors. That's our anchor customer is Stability AI, going into scaling all of their stable diffusion models as well as stable LM models going in. And if you look at a cross-section of customers, we picked these customers for a reason. It's a mix of training on accelerators, inferencing on distributed inferencing on accelerators, training or fine-tuning on Xeons, and inference on Xeons. All real-world applications in production today. And to do this efficiently, there's really no better platform than Ray, and working closely with Anyscale to scale it across both enterprises and startups. Right? Thank you so much for the opportunity. Thank you.
Google. For the longest time, Google has been synonymous with AI. AI wouldn't be what it is today without the enormous contribution from Google. And as many of you know, Google is not only an AI powerhouse, but it's also a powerhouse in building hardware accelerator for AI. They're TensorFlow processing units. And I'm very happy to announce that they are now tightly integrated with Ray than ever. Now, please join me to welcome Alex Pironov, Product Group Manager at Google, and Alex Wang, Senior Software Engineer at Google.
Thank you, Jan, for that wonderful introduction. Hi, everyone. My name is Alex Spiridonov, Group Product Manager for Google Cloud AI Accelerators. At Google Cloud, we are proud to offer you a wide choice of AI acceleration platforms, from NVIDIA-powered GPUs to Google's tensor processing units, TPUs. Cloud TPUs provide a cost-efficient, high-performance, versatile, and scalable platform for training, fine-tuning, and serving large language models and generative AI models. And today, we are thrilled to announce that Ray 2.7 natively supports Cloud TPUs for effortless developer experience. With Ray, you can now easily train and serve LLMs and generative AI models using hundreds or even thousands of TPUs with the same familiar Ray APIs that you know and love. Ray natively supports the new Cloud TPU v5e, which is purpose-built for high-performance, cost-efficient training and inference of LLMs and generative AI models. Now, in his keynote yesterday, Robert emphasized the importance, the vital importance of efficiency and scalability. And that is exactly why we built the Cloud TPU v5e, our most cost-efficient and scalable AI supercomputer. On cost efficiency, v5e achieves up to 2 times greater performance per dollar for training and up to 2.5 times greater performance per dollar for inference compared to the Cloud TPU v4. Those are amazing numbers. And this magic is possible thanks to the combined power of hardware and software optimizations. v5e is also amazingly scalable. With v5e, you can train LLMs and generative AI models using hundreds, thousands, or even tens of thousands of TPUs. And the best part is that you can achieve nearly perfect linear scaling. This is a game changer for training LLMs and generative AI models, because now you can train even larger models even more efficiently, simply by adding more TPUs. v5e is also amazingly scalable for inference. A TPU v5e pod contains 256 TPUs connected with ultra-fast links. And a full TPU v5e pod lets you efficiently serve models with up to 2 trillion parameters. 2 trillion parameters. So you can run inference on the most demanding models without sacrificing performance or cost efficiency. Now, we know that as developers, you want to use TPUs in your preferred way that best fits your development process. And this is where Ray on Cloud TPUs really shines. Ray makes it seamless to train and serve your LLMs and generative AI models on thousands or tens of thousands of TPUs using the same familiar Ray APIs. So let's take a closer look. For training, you can start by developing your model on your local machine and then seamlessly scale it up to train on tens of thousands of TPUs. You don't need to have a PhD in distributed systems. The magic of Ray handles all of the complexity of orchestrating that vast amounts of compute. With just a few lines of Ray, you can get orchestration, scheduling, fault tolerance, auto-scaling, and all the other Ray features that you know and love. Of course, Ray also makes it super easy to fine-tune models using TPUs, using your own data and tasks. And after you are done training or fine-tuning your model, you can take the same code and use RayServe to serve those models to your users. Within seconds, you can be up and running, serving your model on a TPU v5e. And when you're ready to run that same model in production, Ray makes it super easy to scale that model to hundreds of TPUs, so you can handle the most demanding production workloads for your users. At Google Cloud, we love Ray, because Ray dramatically simplifies the entire development experience using Cloud TPUs, from training and fine-tuning all the way to serving. But don't just take my word for it. We have some amazing demos to show you just how easy it is to get started training and serving LLMs and generative AI models with Ray on Cloud TPUs.
And to show you those amazing demos, please welcome my colleague, Alan Wong.
Thank you, Alex. Thanks for giving us such a wonderful overview. Hi, everyone. My name is Alan Wong. I am a software engineer at Google. And I'm excited to show you how you can take advantage of all of these exciting advancements easily using Ray on Cloud TPUs. So today, what I'm going to be showing you is how you can actually use Ray on TPUs to easily train and serve Llama 2 models. So as you can already see, I have a notebook here. And I've already created a Ray cluster using the cluster launcher, and it has TPUs attached to it. So first, I'm going to just go ahead and attach to that cluster. And what you can see here is just some basic code. And this is just a Hugging Face wrapper. You can pretty much see that I'm just trying to request the Llama 2 2 billion parameter variant, and I want to train it. If I were to use Ray data, for instance, to pre-process my data, or if I wanted to do performant live streaming, this is a great opportunity to plug that in here. Point is, this can be pretty much any standard workflow. And what I'm going to show you first is actually how you can take this Llama 2B pre-training and easily run this on Ray on Cloud TPUs. So the first step is actually going to be pretty simple. I just want to make sure that this runs on the Ray cluster in the first place. So as a lot of you know, it's pretty simple. I'm just going to decorate this with ray.remote. As is, this is going to actually invoke on a Ray cluster on a worker node, but I actually want to ensure that this targets a worker node that has TPUs attached to it. So what I'll do is specify resources TPU for. And essentially, because TPUs are a native resource within Ray, whenever I invoke this, this will execute on a Ray worker with 4 TPU chips attached to it. But that's actually not all. I also want to make sure that the code executed can actually take advantage of the underlying hardware. And we do that through the ML framework. So what I'm going to do now is import PyTorch and import PyTorch XLA. And now whenever we run this Hugging Face code, it'll actually take advantage of the underlying hardware through PyTorch XLA. So that's it. Let's actually go ahead and invoke this. So init and run hf.remote. And what you can see is pretty quickly we're able to load PyTorch XLA, and we're able to load libTPU, which are pretty key indicators that we're actually utilizing the underlying TPU hardware. So it's actually that simple, and just like that, I showed you how you can easily train a Llama 2B model from scratch interactively with Ray on Cloud TPUs. Thank you. But that's actually not all. I want my next model to be much larger. I want it to use hundreds, if not thousands, of TPU chips. But how do I do that? Fortunately, Ray makes it really easy for us to do that as well. So I actually have this function, this main function here. And what you can see is pretty much the exact same code you just saw in this notebook. And there's only a few minor changes. I want to train a 70 billion parameter model and a few different arguments. And essentially, now my Ray cluster has many more worker nodes with TPUs attached to it. So basic question is, how can I actually take advantage of all the compute in this cluster? Well, with Ray, like I mentioned, it's very simple. So because Ray actually knows about all of the TPUs that are in the cluster, I can easily say, hey, tell me how many hosts there are. There are 4 chips attached to each worker. So I can easily say the number of hosts is equal to this amount of hosts. And then I can just take this one remote call and just propagate it to every single worker in the cluster. So to do this pretty quickly, I can just pretty much do a list comprehension here and just go ahead and get the results of that handle. So executing this is going to be easy. I wrote this in another file so that I can take advantage of the RAID jobs API. So it'd be something like RAID job submit, Python main, something like this. Honestly, this takes some time to execute. So I just went ahead and did this a bit ahead of time. So as you can see here, I already have this running in the background. We're loading PyTorch XLA, 70 billion parameters. A lot of logs, but you can finally see that we are doing some training at the end of the day. And just like that, it was really easy for me to take the same code I used to train interactively in a notebook, scale it up to 70 billion parameter with hundreds of TPU chips. And this is all thanks to Ray's simplicity and orchestration capabilities that we were able to do this so quickly. So I'd actually love to sit here and wait for the rest of this pre-training to run. As you can see, there are a lot of logs. This might take a few weeks, but we honestly have a pretty exciting day of Ray Summit ahead of us. So let's actually just fast forward to when this model has finally been pre-trained. So serving large models is a pretty unique thing. You generally need a lot of compute in order to run this in the first place, let alone if you have any latency concern, which I'm sure you do. If you're looking for an accelerator option that is both performant and cost-effective, TPU v5e is actually a really great option to do that. But like I mentioned, it's a pretty unique thing. How do I even run this in the first place? It's probably going to be complicated, right? It's really not. And I'm going to show you how. So back to the code editor here. I have this basic Python code here. And generally, the gist is I did all my pre-training in Python on Ray on TPUs. And it should really be really simple for me to express the same thing as a model server. I essentially want to be able to load a checkpoint and send arbitrary inferences to it in batches. And I wrote this all in Python. I would love to actually just stay in Python and not really have to change programming language barriers or switch stacks in order just to serve this. Maybe later, but maybe not as a first step. So fortunately, Ray makes this really easy for us to do as well. So if I were to say from Ray import serve and mark this as a deployment, and then again, I want to target worker nodes that have TPUs attached to it, so Ray actor options TPU4. This is actually already a pretty sufficient deployment. But I actually just want to add in one more thing. Ray already has native integrations with Gradio. So you can see I have some snippets here that I kind of just took from the Ray docs. And if I were to do something like serve run Gradio, then I would have a sufficient model deployment for a Llama 2B model. So as you probably expect, I already did this ahead of time as well. Let's go ahead and take a look at this screen here. And for the fun of it, let's just actually, this is a text completion problem. Let's actually ask like a really simple question. It's live, so I believe the meaning of life is to continually learn and grow. That's a really great answer. So I just showed you how easy it is to actually serve a model using the exact same stack that you used to pre-train it. So that concludes the demo. If we could cut back to the slides. So in conclusion, today I showed you how you can start with arbitrary PyTorch or JAX model code, test interactively on a single TPU, scale it to a production training job with hundreds, if not thousands of TPU chips, then test serving on a single TPU, and then scale your deployment out all using the same exact software stack. I wanted to let you know that actually this is all available on GitHub today if you look up PyTorch TPU Ray Llama. And finally, I wanted to thank Anyscale and the organizers of the event for putting together such a great Ray Summit. It's been a great opportunity for me to meet such an incredible community of brilliant and passionate people. I'm really excited to see what we're able to build together with Ray on TPUs and hopefully talk about it at next year's Ray Summit. Thank you.
Nice job. Nice job. It's so great to see the growing accelerator ecosystem from Amazon, from Google, from Intel, and NVIDIA yesterday that Ray integrate with. I'm really excited to see people build more applications using all these different hardware accelerators. Now, it's my great pleasure to invite Ben Horowitz to the stage. Ben is co-founder of Andreessen Horowitz. Please welcome Ben. Welcome, Ben.
All right, good to see you, Robert.
Thank you.
All right.
It's very exciting to have you here.
All right, good morning, everyone. It's exciting to be here.
Yeah. So there's a lot of questions I'd love to ask you about AI, about Andreessen Horowitz, but perhaps you can tell us a little bit about how you got started and what you were working on before A16Z.
Yeah, well, I started as an engineer many, many years ago at a company called Silicon Graphics, which some of you may remember. It's a great company and a great place to work. But then I went to a company called Netscape, which
Never
was,
heard of it.
yeah. Well, a lot of you are probably too young to have heard of it, but it's kind of the open AI of the day, I guess. I would say the most important thing about Netscape is it was the company that made the open internet the internet. And I think in retrospect, we always think, of course the internet's open. Of course anybody can use it. Of course there's not like a tax from a company on it. And then in the same way we go like, oh, of course, search is proprietary or, social networking is proprietary. But it didn't have to be that way in either direction. And in fact, there was a huge push from Microsoft to make the internet proprietary. And if you go back, if you can get your hands on the first edition of Bill Gates's book, The Road Ahead, which was published in 1995, no mention of the internet, none. And it's not because he didn't know about the internet, it's because he was fielding a rival, which he referred to as the information superhighway, which was known as Microsoft Network. And they had proprietary versions of everything, BBML instead of HTML, and this and that and the other, which stood for Blackbird Markup Language. But Netscape's kind of big contribution was we kind of put in the functionality that the internet needed for the open version to win. So the internet had no security. SSL was invented at Netscape. It had no programming language. JavaScript was invented at Netscape and so forth. And so a lot of that kind of contributed to the open internet that we have now, which I think is kind of significant because we're also at that kind of place with AI, right? Where there's both, kind of forces in various governments around the world, as well as people in our industry really pushing to outlaw open source, which seems like bizarre and crazy. But I can tell you, in the early days of the internet, they outlawed encryption for a while. And we could not export 128-bit encryption. It was completely illegal. It was considered a munition. And we're like, the code is in every textbook. Like, what are you talking about?
Can you expand on this idea of a proprietary internet? Just help us visualize if that had played out, what that would look like.
Well, I think it would look like a lot like the App Store in that Microsoft actually had a kind of a position that they took, and they called it a vigorish. They would get a vigorish, which was like a mafia term, I guess, on every transaction on the internet. So anything you bought, anything you did on the internet, Microsoft would just take a fee, and and you'd go to them and you'd sign up and you'd enter your Microsoft stuff and all that kind of thing, your Microsoft password, and they would give you access, and you'd give them your credit card, and you'd get on that way.
Yeah.
And like a lot of the early internet version, right? You had CompuServe and AOL and these on-ramps, so it sort of made sense. They were kind of dial-up services that predated the internet for consumers. That the industry would be thinking that way. And look, they all ridiculed the internet because it's like, you can't put security in it after the fact. What are you, stupid? Every engineer knows you can't add security, to a protocol later in the day and all that kind of thing. But,
wait, so what pushes these things one way or the other, whether it's the internet or search or AI?
So it's a combination of people and technology. So if we were kind of going on the internet technology that was kind of present when I got on the internet in the late 80s, where you had to call a guy and get an IP address and then edit Etsy host and plug in the yellow cable. Some of you remember what I was talking about. But if it remained that internet, with no DHCP and no SSL and so forth, then the proprietary versions would have had a real running start. And then there's, of course, a network effect. So there's kind of this, is the technology good enough? And does somebody step up to making it good enough if it's not? If you look at social networking, we had a technology called RSS, which was the open version of social networking. Nobody ever kind of did with it what people are trying to do now with kind of crypto and Web3, where you could have a fully functional social networking protocol that would support an open version. And so the proprietary things went out. And then, if you look at what's going on with AI, there are like big AI companies, I won't name names, because I think some of them are here, but who are pushing to like literally outlaw open source. I mean, they make statements like, we can't have open source AI. And look, Mark Zuckerberg, whatever you think of him as a complete hero in the AI world, and that he released Llama. There were a lot of people who didn't want him to do that, both inside the company and the government and so forth. And he had the courage to say, look, we need to live in a world where there's not a tax on intelligence in the way that there's a tax on so many other things.
Yeah, that sounds like a pretty high stakes thing.
I think it's very high stakes, and it also is like information control when you think about how these systems work and what they're allowed to say and what they're not allowed to say and so forth. Do you want that controlled by a company? Yeah. And like the problem with, most companies have great people and so forth, but it's always bad when you concentrate, like in society, concentrating power tends to lead to bad outcomes. And concentrating the kind of most powerful technology we've ever built in the hands of one or two companies doesn't seem like a good idea.
Yeah. And is open to closed the right axis there, or is it concentrated to distributed? And do you think open models are kind of analogous to open source?
I think so. I mean, I think that, look, the more people who can work on them, who can be in the conversation, who can, have a voice in terms of how these things are used. Look, if nobody has all the power, it generally works out well. And if somebody has all the power, it generally works out badly. This is kind of the big lesson we learned in the last century. A lot of in theory, communism was really good. The problem was it concentrated all the power, out of the private sector into the hands of a very few people like Stalin and Mao and Pol Pot and Ceausescu. And it always turned out the same way. It didn't matter if they were good guys or bad guys. That much power, everybody dies. So
yeah, yeah, and it's perhaps in the communism example, it's unintuitive at first glance because
because it's marketed as power to the people,
right?
But it's not. It's all the power in the private sector goes into the government, and then the government is controlled by a few, not the many. And then, okay, what do you do?
And you don't have powerful corporations as a counterbalance.
Yeah, right. Like there's not, powerful corporations or just like more people, like more distributed power.
Yeah.
And they always end up being dictatorships because it just concentration leads to concentration, distribution leads to distribution. So, look, I mean, there are bad people in business, there are bad people in the government, but as long as neither can stomp out the other, that's better.
Yeah. How did you decide to start a venture capital firm?
Well, it's the best entrepreneurial idea that we had at the time.
Were there other things in contention?
Yeah, no, I mean, I think, so a lot of it was based on our experience as entrepreneurs. So, look, as a founder trying to build a company, what you find, and this from experience, you don't know what you're doing, like it's like, oh, I invented this thing. I know how to build a product, but I have no idea how to build a company, let alone run a company, and so forth. And it always felt like to us that, oh, we'd get that from our venture capitalists, like we'd get some help. But that wasn't really how venture capital worked. And we thought, well, that's weird that they're just going to give us the money and then like some weird advice about how smart they are and how our product should work, which they didn't know anything about. Like, how about like some like help in building a company? Like, how about a network of like people, customers, executives, people we can recruit, call, so forth, can you help us with DC, all that kind of thing. And it just didn't exist, so that was the idea. And so we want to build a firm for a founder to learn how to run their own company.
And has that vision, was that essentially how it played out? Or did it, did you take it in new directions that you didn't anticipate?
Well, that idea worked, which is kind of why I'm here now, I guess. Because if it hadn't worked, you'd be like, who is that guy? And I think, so the original idea was just that. It was like we were going to have a better venture capital product, and that would enable us to win deals. And we didn't even really think that much about picking the deal. We were like, look, if we can win the best deals, then we'll just do that. And that, look, it worked out pretty well. But as we've grown, we've really developed much more focus and expertise and capability around very specific things like AI or crypto or bio or games or any of the kind of fields needs its own network, its own level of expertise, its own capability to help you build that kind of company.
Yeah. How is investing in AI different from other kinds of investing?
Yeah, so I would say the biggest thing that's different is the founders are different. And what I mean by that is, so if you look at, there's a lot of people who I would say don't understand the technology that well that are making investments, and they don't have these problems probably. But if you understand it, the challenge is the thing that is very interesting now are these foundation models. And the people who can build foundation models are the people who have built foundation models, if that makes sense. So if you've not had a very nice, generous, magnanimous company like Google give you a lot of money to go train a model, see what's wrong, make adjustments, learn how it works, and we just give you some money, chances are you're not going to build a model that's very competitive. That's just the way it is. So the people who we fund end up being researchers, as opposed to PhDs in AI and people have done research for many years, as opposed to in the past it's been, it might be a product manager or an engineer or somebody with a different kind of background and a different kind of, maybe capability on how to run a company. And then when they start building the company, most of the people who get hired are similarly AI researchers or, I think Anthropic is half physicists, which is that's not what we're used to funding. So it is very different in that way.
I'm a big fan of researchers.
Yeah, there you go.
Yeah. So does, everything happening in AI today, this is not the first technology wave you've participated firsthand in.
Yeah.
Right? You saw the explosion of the internet, other things as well. Does this feel different? Are there lessons we can learn from the internet?
Well, so there's things that are the same, but there's a lot that's different. So, one, just technologically, there's, the history of computers is a history of of computing is the history of computers and networks. And the internet was clearly a network, and AI, I think, is clearly a new kind of computing platform. So they're fundamentally different in that sense. The thing that's the same, very much the same, just from being around it, is in the beginning of the internet, every single day you'd be like, whoa, look at that, somebody built that. Oh my God, I can't believe they built that. And AI is very much like that. So every day there's some new thing that comes out that you go, wow, I can't believe it can do that. And so it's really exciting in that way. I think it's different in that, one, there wasn't nearly as much government scrutiny on the internet as there is on AI. And then I would say companies are way more on board, big old companies with AI than they ever were with the internet in the beginning. The internet, they were so not on board I'll give you just two kind of funny examples. The first thing they said was like, screw the internet, we're not doing that. We'll maybe use HTTP and HTML inside our company. We'll have an intranet. And then they're like, well, we do need to talk to partners, so we'll have an extranet. And and then finally they're like, F it, we'll do the internet. But even then, at Sun Microsystems, which was like the big Unix company of the day, they banned the internet for employee use, and I think it was 95. And at the time, like I think Eric Schmidt was the CTO of the company, so like they had like real guys in the company. But that the internet was like, nah, that's not for business. That's just some porn.
I see. I mean, what do you think is the reason is this just businesses maturing, that they're adopting new technologies faster, or?
Well, I think partly it's because, the internet, information gets disseminated so fast that it's hard to miss. When the internet came out, you would have to read about it you could read about it in some weird magazine. There was a newsletter called The Red Herring that you could buy, but that was and there was Dr. Dobbs, but there's not that much technology publications in those days in the beginning. And so it was easier to miss. And then if you watched it on TV, some of you have seen the funny clips of the internet with Bryant Gumbel and so forth going, is it a post office? It sends email, is there a stamp? That kind of thing. And so people kind of dismissed it at that point. And they also looked at it for what it was, as opposed to what it was going to be. And, I remember in 95, we went to see all of or maybe it was 94, we went to see all of the big magazine and newspaper publishers and say, hey, you ought to invest in Netscape because this internet thing is going to affect your business. And they were like, you're an idiot. Nobody's going to use that thing. It's never going to read it. You need paper in your hands and all that kind of thing. And so none of them invested. I'm laughing because it's kind of funny in retrospect.
I mean, the internet had a few, maybe more than a few big winners like Google and Amazon and other companies. Does the way that played out affect or inform how you think about how the AI ecosystem will evolve and who will be the winners there?
I mean, somewhat. I think it's the same, but it's different. So, you can't take too much into that. But look, the very early days of the internet, the kind of most promising company by far, I think, was eBay. And then, Yahoo was probably the other one that had all the momentum in this period of the internet, that we're in now with AI. And those weren't the biggest. Amazon, if you go back to, I think it was 2001, Barron's wrote a huge takedown piece that said they were worthless. And then Google, didn't get started until 98. And when Google went public, I think they were worth about half of what Yahoo was worth. So people didn't have a great gauge on who the big winners were going to be. Certainly, even later than this stage, but not at this stage. And I think with AI, that's true too. What's going to happen? What's going to happen with regulation? How are the models going to evolve? Do we reach an asymptote on training scale or not? Looks like not right now, but we'll see. And so all those kinds of things, I think, will play into which companies end up being, super important 20 years from now.
That's a great point. You mentioned there was more, or there is more regulatory scrutiny in AI now than
Way
in
more.
the internet.
Yeah.
What do you see as the opportunities for regulators to either get that right or to screw it up?
It's hard to imagine them getting it right. Just if you look at, everywhere there's been heavy regulation, there's been a lack of innovation. It's funny, once in a while I'll go to one of these kind of events in Europe and what have you. And in Europe, they always say, we're not the leaders in innovation, but we're the leaders in regulation. And I always go, you don't realize those go together? like it's very tricky in the early days. I don't know how I would regulate it, right? Like, and I know a lot more about AI than anybody in the Senate. And so it's pretty complicated to regulate something that's evolving so fast. And I think that's that's the danger with it. I would say that if you were going to regulate it, and this is what I say, to my friends in Washington, D.C., like if this was nuclear, because everybody keeps comparing it to nukes, which is, I think it's a little different, but okay. Would you regulate the bomb or like refining plutonium, or would you regulate the physics? Physics is illegal. And what I think a lot of the people are advocating for is to make physics illegal or require a license to do physics, as far as AI goes. And I think that's the worst thing that you could do. Mm-hmm. I think it's fine if you go, look, there's so many things that are illegal to do, like you can't publish how to make a bomb or how to kill yourself, or like that's illegal already. And so it should be illegal for AI, and that seems fine. But the existing set of laws works reasonably well. Now there is a new kind of thing or a new issue, which is, how does it affect copyrights? And there's kind of copyright, and I wrote something and the AI read it and got smart and said something totally different. That doesn't seem to be like a real violation, but you could imagine a regulation that made it such. On the other hand, I'm like, I recorded Drake's voice and made a song, and I said it was a Drake song. Like, that does seem like a violation. And so there are those kinds of issues which for sure are going to have to be dealt with.
Yeah. Do you think the way that some of these issues you brought up are resolved, will have big implications for just the rate of progress?
Yeah, for sure. For sure. I mean, I think that, look, one of the things that I think it was at one of the board meetings I was in, maybe it was a Databricks board meeting, but like one of the things that people said is, like we could be in the consumer AI Napster moment, in that like the government could turn around and just make this all illegal tomorrow, because it basically slurped in the internet. And oh, by the way, you can get it to do a lot of privacy violations. For sure, it's like way outside the bounds of what the EU allows already. Like I ask it about me, and it tells me all kinds of stuff, and I'm like, I didn't authorize you to do that, and these kinds of things. So you could imagine if the regulation went a certain way that like they would just go, okay, you are so liable for what your AI says in terms of privacy, copyright, if you've read anything that somebody didn't give you permission for, that it's just all illegal. And you could never actually have a business because you'd get sued out of business. So like that could happen. And like I said, like Napster, I think Napster was a good analogy because everybody who's using Napster is great. They wanted to pay the music company for licensing deals and so forth, but the whole thing was deemed illegal and shut down, and then things evolved in a kind of different fashion.
Yeah. You mentioned, it's still early days of AI. It's a little early to see, to say for sure who the winners will be.
Yeah.
But when you think about the different, you invest in a lot of different layers of the AI ecosystem, like infrastructure, LLMs, applications. Do you feel like there are missing pieces in the ecosystem, places that you would expect to emerge or you would want to invest in, but hasn't seemed to emerge yet?
Yeah, well, there's definitely like many missing pieces. Like, certain things are more complicated than they will be in terms of, doing embeddings and this and that, and just at the tool level. And then, when you get into like an enterprise environment and you actually have things like access control that people care about and so forth, I think that's like very difficult today in an LLM world. So there's many, I think there's many things to get built. And then, but the fundamental technology is moving too. So as that advances, there will be kind of more things. And then the interesting thing with this technology is like the technology is like pretty good at, like you can, we keep talking about prompt engineering and like how that's going to be really important, but then like the technology is pretty good at prompting itself. You can just ask it, hey, could you ask yourself in the right way?
I'm always amazed when you can.
Yeah, like it's really weird how good it is. Like you got to keep getting more and more meta and just like let it figure it out.
Yeah, I'm always amazed when you can ask these things the same question in a slightly different way and just get, tell it to answer as if it's Albert Einstein, and it just does way better.
Yeah, and we have a company we invested in called Audiogram, and like if you look at their usage, it's really interesting because a lot of it is just the same prompt over and over and over again, and it's generating a different picture off the same prompt. So it's like, I'm not even going to change my prompt. I just want to see, give me all your ideas. Like I want to see 100 of your ideas on this prompt. And so it's hard to even imagine where it's going to go.
I wanted to ask you about the chip shortage. We just heard from a bunch of companies building hardware accelerators. And you mentioned that there was some parallels with the internet as well.
Yeah, so there was like a massive bandwidth shortage if you go back to 1998, 1999. Everybody wanted onto the internet, and there was like dial-up and copper wire and no fiber anywhere and all this kind of thing. And so just to give you an economic idea, so in like November of 1999, I think bandwidth was $1,500 a megabit was what you paid for bandwidth. And by the way, you had to buy it on 3-year deals. Sound familiar? And then by early 2001, it was $50 a megabit.
So 1,500 to 50.
50.
Yeah.
And there was a massive wave of bankruptcies among telecom companies coming out of that. And bankruptcies and fraud. So I think probably half of the telecom companies in the US went bankrupt. So yeah, it can happen very fast. You can go from shortage, like, when are we not going to need more bandwidth? Never. So like, let's buy a lot of it, to, we have more bandwidth than people need at the moment. And I think that, in GPUs, that's a real possibility, I'll just say.
Yeah.
I try and buy for shorter terms than 3 years if you can.
Yeah, so does that mean it's a good time or not a good time to start a chip company or a cloud provider?
Well, it's interesting. 1999 turned out to be like a really bad time to start a telecom company. I don't know if that will translate. I do think, the fact that we're using, chips that we made for like graphics and video games and then applied to like Bitcoin mining, and now we're applying to this. Like maybe there's, I don't know, I suppose there might be something that somebody could figure out that would be more dedicated. But I also think like if you knew it was going to be the transformer model forever, then that would kind of inform you maybe in a different way.
You could optimize for that much more confidently.
Yeah, then if the models are going to change again, and there's obviously lots of debate on that.
Yeah. I mean, so investing in AI can be very capital intensive, right? Because you're training these models, spending hundreds of millions of dollars, or at least maybe
billions, billions in some cases, yes.
Yeah. How does that factor into does that change the calculation for investing in these kinds of companies?
I think that if you're gonna, that's why there are only a few like extreme, large model competitors right now. But I think that that'll move around a bit, particularly as the GPU shortage alleviates. And we're seeing actually interesting things, with very large models being built in the Middle East where power is extremely cheap. So there's that kind of factor too. So we'll see. It's a little hard to predict, but probably so.
So one topic that I know is near and dear to your heart is management. You've written a lot about management advice. Mm-hmm. Can you, first of all, share anything about how you became such a great manager?
Yeah, by being a bad manager.
Yeah.
Look, I think the only way to learn how to actually run something is the hard way. I mean, like I wrote a couple of books on it, and hopefully they're helpful, but you can't quite learn it from a book in that it's like trying to learn how to play NFL quarterback, by reading a book. Like it's all fine, and I'm sure it could be helpful, but once there's like a 300-pound person running at you really fast, going to kill you, like it kind of changes how you process information. Yeah. And management's a lot like that, when somebody is really angry with you, who's a high performer or whatever, two people are fighting with each other that you like, or, like it gets like the dynamic nature of the situation and the kind of specific situation that you're in changes things. You do need some experience to learn how to deal with that.
Yeah. We're not always good at predicting what tasks will be easy for AI and what tasks will be hard for AI, right? Like many people expected solving math problems to be easier for AI than writing poetry. Yeah. But it appears to be the opposite. So I'm curious, where do you think management is hard for people? How do you see that playing out for AI?
The very easy part is kind of like the theory of management. Like you need maybe like a 7th or 8th grade education in math and like being like reasonably smart, and you can understand like the theory of it. It just gets difficult because it gets so personal so fast, and then you have everybody has an individual personal interest and a company interest, and like once you start running things, you find that the company definitely doesn't always come first for everybody. It might come first for you, but not for everybody in the company. And then and that's where the complexity is. So it depends how good AIs get at, I guess, understanding humans. If in fact they're managing humans, if they're managing other AIs, then that could work out really well.
Maybe it could work extremely well. Yeah. Ben, this has been a pleasure.
Yeah,
thank you so much.
A lot of fun.
Please thank Ben.
Yeah.
Thank you, Robert. So next, it's my pleasure to introduce Brian McClendon. Brian McClendon is SVP of Engineering at Niantic. Please welcome Brian.
So thank you very much. So as I said, my name is Brian McClendon, and I work at Niantic Labs. And you may know Niantic Labs from the game Pokemon Go, which I am guessing at least you and some of your children have played. But today I want you to think about Niantic as both a mapping company and a software development platform company. And that's where I spend most of my time managing most of the engineering in those categories for Niantic. But I thought I'd talk a little bit about how I got here. So it's interesting, I overlapped with Ben at Silicon Graphics, so I've been around a while, like he has. But my experience in big data really began with Keyhole, which was the precursor to Google Earth. And so building a satellite and aerial imagery of the world database is very hard. And we had a proprietary data pipeline that would take in all of that data, blend it together, get the edges right, figure out what was the highest resolution, and then present that to the user. And so that was my early exposure to big data. My career continued, and I also worked at Uber and led the Michelangelo team through that 1.0 experience. However, it's far cooler today with 2.0 and all the things you saw earlier. At Google, I also oversaw the development of Street View. And this was another big data challenge for Google because we were collecting imagery every few meters over millions of miles. And this data set was over 20 petabytes of imagery. And again, the data pipeline was proprietary. We had to figure out how to align it, geo-orient it, and use that information to then present a great user experience to users who could drop in and see their house. The challenge when we did that was that they would look at the map associated with that picture, and the map would be wrong. That was because Google was licensing its data from third parties, and what we discovered, I think before anybody else, was that licensed map data was not very good. So we started a project called Ground Truth and built our own maps at Google. And we used GPS tracks, we used government road data, as well as this Street View data to build our first maps of the world. And a lot of it in the early days was elbow grease. We had operators that would help draw the maps and improve very ugly pictures like this into smoother geometries. And so this was a relatively manual process at the time, but you can imagine today it's all computer vision. But that was not the hardest problem, nor the biggest mistake with maps at the time. Geocoding, where is this house address? Well, we had Street View now, so suddenly people were dropping in and looking at pictures and saying, your addresses are all wrong. I'm supposed to go to this house, but I look and the picture's wrong. So they were directly comparing the map data. We decided to automate this process. We took all the Street View imagery and we extracted anything that kind of looked like a number. And we then took it and sent it to the best software at the time, OCR software. And it got about 35% correct, which was better than nothing, but not good enough. So we actually then sent it to manual operators to type it in. And they had to deal with all sorts of crazy fonts. And there's no real rules or regs on how to display your house number, at least in the United States. And so figuring out what these numbers were was a very manual process. We couldn't afford to do that. It turns out that's pretty expensive also. So how many of you remember this picture? So at some point in the early 2010s, you were faced with typing in some squirrely letters on the right there and some numbers. We knew the answer to the squirrely letters, so that proved you're human. That was the actual recapture result. But you gave us the answer for the number. And we did that 2 billion times, and that is why Google Maps is better than Apple Maps. So what do you have when you have 2 billion pictures and 2 billion labeled pieces of data? That's a big data problem. Now, if you look at the year at the upper there, this is 10 years ago. So this is actually ancient history. But this was TensorFlow, the early days, also known as Google Brain. Some intern came over and said, hey, do you have any good data sets we can try on this secret new project? And so we threw over the 2 billion pictures. And at the end of the summer, we got back a system that was better at recognizing those pictures and entering the numbers than any 2 humans combined. And that power made it completely automated for Google to drive down the street, collect the imagery, and then create the accurate geocodes that you find in Google Maps today. So that brings me to my actual job here, which is at Niantic. And our goal is to inspire people to explore the world together. And you may know that we are a game company, and yes, we are, Pokemon Go, as well as several other games. But I'm going to talk a lot about mapping today and a visual positioning system. So our goal is to collect data from users and help them locate themselves precisely around some of these things that you might remember as Pokestops or what we call wayspots today. And to generate these high-quality 3D models of these sort of islands of the map. And our goal is to cover the world with this data. And it looks really great there with some dots. We have 20 million places that Niantic keeps track of, and over 2 million of them are already fully scanned and ready to be mapped. Now, this is what San Francisco looks like today. So we have several hundred or a few thousand locations in San Francisco. It's one of our more popular locations, but we have a lot of work to do there. So how did we build this system? Or actually, how do we apply the system? So VPS allows a user to stand near a place and understand everything about the geometry and precise position of themselves relative to the location. So the pose, like where you're pointing your camera. And this enables some crazy applications, apologies for that one. But it also enables some very interesting augmentations of the real world. So augmented reality and virtual reality have been greatly enabled by those GPUs that Ben and were talking about. And things like this are only possible because of the power of these GPUs that are now both in phones and in the data pipelines that we all know and love. So we collect this data with these scans where our game players actually actively go out and collect some videos and upload it. We then build our maps, and then we serve our visual positioning system. And all of these are very compute intensive. So our mapping solution is crowdsourced and constantly refreshed because our game players keep going back to many of these locations as part of their experience. And it's available to our players and to developers in those same places because that's where they're focused. And our differentiation is we're below 10 centimeter precision in our position and pose. So what did the back end originally look like? Well, like many of you before Ray, we had our own proprietary pipeline, and it had millions of lines of computer vision code that were used to build the maps, process the scans, align the maps, and also to run benchmarking. And we had 10,000 lines of code just to do the orchestration. We also had research teams, and they would work in their environment. They would throw this C code library over the wall, and then we would run it on the pipeline side and be surprised when the results were not the same as what they had just handed to us. So we had this inconsistent environment problem. And so it was slow. So we discovered Ray, and there's a presentation from Chi Zhu later today that goes into much more depth on this, but he was the one who introduced it. But our whole mapping data pipeline team has done a lot of work to bring this in to convert our system. And the impact is incredible. First of all, 1,500 lines of code to completely rewrite the whole system, versus 10,000. Much more reliable. But more importantly, developers are able to run exactly the same pipeline on their own machine. It can synthesize the same pipeline running on a single machine and produce exactly the same results. So the cycle time improvement has been incredible. Production speedups. So here's the actual impact. For every one of our processes, we had significant cost reductions, anywhere from 30 to 70%. The latency from the time we got a scan in to the time we shipped it out was reduced by 3/4. And this is, the scan pipeline actually does the anonymization that we both did at Google and we also do at Niantic, which is to blur faces and license plates. And it's a very expensive process. And implementation much easier. Now our mapping pipeline, 50% faster, and it's still being improved over time. And finally, the developers, the computer vision developers, when they're running it on their own machine, are now able to run benchmarks to check their own results and speed it up by over 5x, which is incredible from a performance and productivity perspective. So Ray has had a huge impact at Niantic, and I want to thank Anyscale for developing it, and we're going to continue to use it over time. So I know I said we're a mapping company, but I'll finish with this. We launched Monster Hunter Now 5 days ago, and if you remember the days of 2016 in Pokemon Go, this is as close as it's ever going to get. We have had a huge, especially in Japan, but even in the United States, a huge take-up on this game. It's in some ways similar to Pokemon Go, but in other ways very different. And I would recommend, if you have a chance, download it, give it a try, and thank you very much.
Thank you, Brian. Thank you, Brian, for the energetic presentation. So before we start the next panel, a quick question for the audience. So raise your hand if you consider yourself a system or infrastructure engineer. Here we go. Let's round of applause. Because today's panel is exactly about you. You're the heroes behind all the AI applications running today. So let's welcome to stage 3 engineering leaders, and we'll talk about building the next generation AI infrastructure. So to begin today's discussion, my first question I'm really curious is that how AI is used in your company and what do you think are the most valuable AI use cases? And since Albert already covered AI at Uber in the keynote, so the question is for you, Selwan and him.
Oh, for me or for?
So let's go Selwan and him.
All right,
Yeah.
cool.
Yeah, so our mission at Pinterest is to bring everyone the inspiration to build the lives they love. And it's not easy to pinpoint just one AI use case that brings the inspiration that people are looking for. In fact, it's a fairly complex combination of multiple AI use cases. So instead of picking one, I'm going to give you a very high-level overview of how these AI applications interact when you visit the Pinterest website. So as a pinner, you're looking for some inspiration to do some stuff in real life, and you're searching for ideas on Pinterest. You might land on home feed search, related pins, or visual search surfaces. And when you get on these surfaces, what happens is we need to retrieve machine learning features that summarize the contents, summarize the users, and often these involve fairly sophisticated representation learning techniques. And then we have to go and search for whether these contents are safe for our users. And then we go search through our billions of corpus to figure out the top candidates that the pinner might be interested in. And these involve things like two-tower retrieval, lightweight scoring applications. And then we have to rank them, to figure out the right promoted contents to show. And ultimately, all of these applications work together to bring the inspiration that pinners are looking for. So yeah, it's hard to pinpoint just one AI use case, and all of these work together to bring the nice experience we have.
Great, that's inspirational. So Hing, anything to add from DoorDash?
Yeah, for DoorDash, there are 3 use cases I want to share, a quick description. One is whenever users land on the homepage of DoorDash, you see a lot of the feed as well as the recommendations and ranking and such. It's a huge part of our platform, and it drives a lot of conversions for us. The second one is about the ads and promotion, so ads targeting and such. The third one is very dear to our company as a logistics company, is our logistics engine, right? Assigning the right order to the right dashers at the right time, so everybody get the food at the right time that we expect. And I think the commonality between these 3 use cases are essentially they all need a lot of data. They need like state-of-the-art DNN models, as well as low latency and high QPS. So it's quite interesting. So
Great. I hear a lot of great insights on really critical problems like recommendation, ranking, prediction. So how about generative AI and including large language models, right, Hing? Do you see any interesting new use cases?
Okay, yeah, at Uber, we deeply cared about making our employees more productive and creating magical user experience. Like Albert shared, we have been trying Copilot for helping our software developers to be more productive. We are generating better queries for other employees at Uber to improve their understanding of the data. And also we are working on projects to making our user experience more magical. That I think gradually we'll be able to share more as time goes.
Great. Hing?
Yeah, this is definitely a very exciting area, and like many companies, we're exploring various kinds of use cases. But broadly speaking, there are 3 areas that we're looking to build interesting applications in. The first one is an assistant. I think there's widely known use case like a chatbot. But imagine on a DoorDash platform that an assistant can help you find the right kind of food or lunch or dinner that you would like for a particular weekend, for example. So that's a very prominent use case there. And then the second one is about the content generation, right? Which is what Gen AI and ChatGPT is really good at. For us, it's about like helping our merchants to generate their menu items. You probably saw a demo from Adobe earlier. So generate those very immersive menu food items that encourage people to order food and things like that. And I think the third one's quite interesting. It's about extracting like structured information from various sources of data that are either images or in text. So given a menu items, we want to extract like what kind of information is in there, what kind of food items, what kind of type of food that is, and what kind of ingredients are in there, and the price and such. So broadly speaking, there's 3 categories that we're looking at.
It's a great combination of internal and external use cases. Thank you. Siwan, anything to add?
Yeah, so Pinterest being a primarily visual inspiration engine, we have a lot of exciting things that's brewing in our labs. It's a little early for me to share today, but I can tell you that we're putting a lot of thought and care in carefully blending these Gen AI and large language model capabilities into the experience that we offer. So please stay in touch and up to date with the Pinterest product updates, and soon I think you'll be able to find out.
Yeah, really looking forward. So with that context, right, about AI at your companies, now let's turn to the main topic of today's panel, AI infrastructure. And this is what you live and breathe every day. So I think personally, I'm very interested, I think the audience must be, to hear from you firsthand. So how do you think AI infra has evolved in your company, and what are the main challenges you have been observing? So this time, let's start with Siwan at Pinterest.
All right, yep. This is a really deep, sophisticated topic. And the important thing is that the evolution of AI infra is not a linear process. So it's not easy to summarize it in a few sentences, but I'll do my best in putting applying some kind of framework to help you all understand the evolution of AI infra. I like to break it down into two categories. First, the evolution of the infrastructure, and then the evolution of our standardization efforts. And when we look into how our AI infra evolved, the order in which we go and tackle these problems is to really unlock new capabilities and to allow ML engineers to blend machine learning into our product experience. And when we build out these kind of web scale businesses, the very first thing needs to be that, hey, these ML models need to be servable at scale. And that's exactly why we went ahead and tackled the machine learning serving infrastructure problem first. And this was in the beginning primarily a distributed systems problem, right? Thinking carefully about where to put the cache, how to route the requests, and et cetera. And this allowed ML engineers to build models and actually bring them to our pinners. Second type of AI infra that we then went ahead and tackled was the training infrastructure. And this involves things like, how am I going to put this training script onto GPU number 012, and how to persist the logs, how to schedule things. And that was basically what we went ahead and tackled next. And then the last category of the infra that we went ahead and solved was data related. Feature store, training data set management. So as you can see here, although it's not, in reality, it was not a linear process. It went things like serving, training, and data-related infrastructure. And then if you look at the evolution of standardization, it actually goes in reverse of this order. And that's because when you don't have like a unified infra solving each domain, you have to rely on standardizing it a little bit so that you can keep things under control. And that's why the first level of standardization we did was to standardize the data formats, how features are represented, how the training data sets are represented. And what this allowed is, although perhaps feature and data infrastructure for machine learning isn't fully unified, it allowed the machines to talk the same language. And I mentioned before, Pinterest is a combination of multiple AI models and applications. When you standardize how features are represented, data is represented, now these models can talk to each other, and we can combine them to provide a sophisticated experience. So that's why we standardized the data formats. Next, we standardized on the training and serving framework. So we standardized on Torch. We invested in ensuring that when ML engineers train models using PyTorch, we can take it as is, and then we can put it on our serving cluster and make it servable at scale. So now, the last step of standardization, and this is exactly what we're looking into now, is the AI runtime. And we like to call this the scale first, learn last problem, right? In machine learning, we as AI infra people, we want to prevent cases where ML engineers and scientists come to us with models that we just simply don't know how to scale and serve. So often, when we look back, we found out that we've been resorting to these rigid frameworks that are often configuration-based, that are very hard for your ML engineers to use at times. The thing with configuration is that inherently they reflect our understanding of the past. It's kind of like refactoring code. You see the same code 3 times and you're going to pull it out into a separate function. Configurations and frameworks are kind of like that. And that's why exactly we're looking into Ray, to get rid of this kind of rigidity from machine learning development and bring the power of development back to the machine learning engineers, so that when they quickly try out new ideas, we know that it's going to be scalable. So, and that's what we also want to call as, learn fast and scale last. And that's exactly the kind of paradigm that we would like to enable.
Great. Let's continue with Hing.
Yes, there's, I think, there are similar themes that I heard there, standardization, scale, and such. For us, our infrastructure has evolved quite a bit in the last probably year and a half. And partly due to like the growth of the company, the ML community, the growth in that, to reflect the number of the products that we have to build, and the diverse sets of use cases that we now have that we didn't have before. So evolving to building the infrastructure with standardization. But I'll add on top of that in terms of being mindful about the efficiencies, right? When we're operating at scale, cost is one of the aspects. So we're constantly looking for ways to improve parts of our platform that usually have to be used at scale or support large volumes of features and such. Also for us in our journey is moving toward DNNs, large-scale DNNs. That's where GPUs come into the pictures, into that. So how to use that efficiently, it's always on the top of our mind. So yeah.
It's great. Zhitao, how about the situation at Uber?
Yeah, to continue on the topic of standardization, I think I realized that standardization at different phases could mean standardizing on different things. Uber was one of the pioneers who created the concept of feature store. And then we use feature store to standardize how we process and serve features online for those thousands of models Albert mentioned. Later, we are standardizing on machine learning frameworks. We standardizing XGBoost to serve tree models. Later, deep learning take off. So we move the modeling to also support various type of machine learning models, TensorFlow, PyTorch. We also standardize our model serving so that we have one consistent, unified platform to serve all Uber's models in a consistent way. Later, we realize safe deployment is an important thing. So the team invests a lot of time since last year on standardizing on safe deployments. All these things meaning the definition of standardization is also evolving with the business, evolving with the priorities with us.
It's great. So what I hear a lot is, with the fast growth of the size and complexity of data and model, infra teams are really striving to build common tooling, common abstractions to keep things under control. Right? So now comes to my favorite question. So because I know that Ray, in the past year, Ray has been used in AI infra in Uber, DoorDash, and Pinterest. So I wonder, in your mind, what do you think are the most significant values Ray has brought to you? And this time, let's do something a little bit different. I'll give each panelist a piece of paper. Can you write down the one word that comes to top of your mind? And we'll show the words. And just to be clear, I didn't tell the panelists what to write. All right, I'll count to 3. 1, 2, 3. Ready? Let's show. All right, so from left to right is unified, leverage, and velocity. Happens to be 3 different words. I thought it could be the same. So let's dive into details. So this time, let's start with you, Zhitao.
Yeah, I see Ray help us to unify things on multiple layers, just to offer at least 2 of them. The first is Ray has a great support on containers, Kubernetes, all these things. It helps our machine learning platform to build on top of a more unified compute infrastructure that Uber provides. And that brings a lot of security compliance, standardization, efficiency, opportunities of sharing the resources with the rest of the Uber. The second is Ray help us to provide a unified platform so that we can do all kinds of machine learning there. We have the smallest machine learnings from models like linear regression to decision trees in XGBoost to various type of deep learning frameworks like PyTorch, TensorFlow, and now to the new large language models. Our team actually going to give a talk this afternoon, and 2 engineers will talk about our journey for bringing this unified platform to also cover large language model and dealing with the challenges there. But you can see we are starting from the smallest machine learning models to the largest machine learning models with many orders magnitude different in the middle. And we still manage to run everything on a unified platform. Those small cases are still very important. They carry critical business impact for Uber. So this is why we are pretty grateful about all the standardization this enabled our team to support these cases with a relatively small team.
Yeah, that's really a great utility. If you think about it, from linear regression with a few parameters to the model, so it's nearly 100 billion parameters.
Yes.
And that's the way to unify, to show the value of being a unified platform. So now it's your turn, Hing.
Yeah, our journey with Ray started last year. I was in the audience last year attending this conference, and we got really excited about hearing a very interesting presentation from Uber last year about their hyperparameter tuning presentations. So timing-wise, it's great because at the end of last year, we started looking into how do we modernize our machine learning infrastructure and learning all the great things about Ray and adoptions and such. We explore and evaluate Ray earlier this year. And as part of that effort, we decided to adopt Ray as like our foundational layer of our infrastructure. And we did tons of work over the last couple of quarters. We have 2 presentations. One was given yesterday. And this afternoon, I think we have another presentation that was going to be giving on building our inference, our prediction platform on top of Ray serves. So this is a great leverage story for us that we're able to build a platform on such a solid foundation. So we can move fast, right? We can focus on things that matters more than most to like our internal customers of the ML platform team and how to integrate that into our DoorDash infrastructure. So, yeah.
It's great. So basically, you're able to do more with the smaller team.
Exactly.
That's great. We're going to make this value even more, even better. Yes. So yeah, you're the last one for this question. Velocity.
All right. Yep. So it's been a little less than a year since we started to look into Ray. So we spent the first 6 months trying out new things in a relatively smaller scale, validating our hypothesis and ideas. In the past 6 months or so, we've made a lot of progress in introducing Ray into the Pinterest ML ecosystem. And the reason I chose velocity is, it directly maps to why we started to look into Ray last year. And it's for 2 reasons. So first of all, was the training, and a lot of users started to report that, hey, my training's slow. So we looked into these problems and we noticed that, hey, the data throughput cannot catch up with the speed at which the model's learning and how the GPU is processing and performing backpropagation. We looked into it and we realized that in order to solve this, we need a solution to efficiently manage a heterogeneous set of resources. There's going to be CPU resources involved and also and GPUs. And we need some solution to horizontally scale the CPU workloads so that the data processing and loading can catch up with the speed of the GPUs. And that maps the velocity of training, right? We need the training to be as fast as possible. If it's fast, then the cost is going to be lower because the machines are going to be working for less amount of time. The second thing that we're looking for in Ray is the developer velocity. And when we did a quick retro and looked back on how ML engineers are doing their day-to-day work, we found out that they have to learn and utilize so many different tools and languages. You have to learn Spark, you have to learn Airflow, you have to learn PyTorch, you have to learn some model registry, and a lot of different APIs. And not just the fact that you have to learn them, but actually in order to get stuff done, you have to jump across these tools. And for each of them, you have to unit test things and integration test and figure out the right configuration. And this was a very time-consuming process. And Ray allows us to put all of them into one framework, AI runtime. And that's also been quite helpful for us.
Sounds great. Yeah, the CPU, GPU point is really powerful. Also reminds me of what was just discussed about not only money, but shortage of the chips. And hope we can help that by offloading part of the compute efficiently to CPUs. Now my next question is a little bit selfish because every year's Resummit is our checkpoint. Red team will look at the back and collect users' feedback, and we plan for the next year. So in terms of making our roadmap, what are the top on your wish list of enhancements, things you want Red team to add? So let's start with Sewan.
All right. So first of all, I talked about velocity. We really care about enabling ML engineers and scientists to move fast. And to do so, I think we need to enhance the interactive development experience on Ray. And whether we like it or not, making some edits, running it, killing it, running it again and killing it, that's just a natural part of software development. And we want Ray to help us do this faster. I can quickly try things, kill it, and there's going to be a lot of different tools. For example, perhaps we can better integrate with the Jupyter ecosystem, because it is the de facto interactive development IDE at this point. So that's one thing that I would like to ask from Anyscale. Second thing, it's a little bit similar, but the one is on debuggability. Ray, ultimately, it's a distributed systems framework. And when we decide to adopt Ray, into our AI infra, the ideal scenario is that we can give a clean slice of our pie to Ray so that it can bring value to our users. What that means is that users have to be able to debug in a self-serve way. And we need a way to bridge the gap between the systems knowledge that the ML engineers and scientists have and the systems knowledge that these kind of frameworks require. So perhaps it can be smarter about suggesting, hey, your memory is not enough, your block sizes are too small or too large. And actually, yesterday, on that note, the Anyscale Doctor, that kind of tooling seemed like the perfect fit on this front.
Great. Continue to Hing.
Yeah, I think +1 on some of those aspects that you mentioned there. At a high level, I think continue to push the boundary on efficiency, scale, and future-proof that Robert talked about. I think that's very important to a lot of companies. And the second one that I would mention is about, again, in the theme of leverage, right? Obviously, a lot of us are going to start building LLM applications. Reducing the inference latency for LLM models is going to be very, very helpful of how do we, as a community, figure out how to optimize those. I know Ray has a lot of integration with the open source libraries like DeepSpeed and things like that. But I think continue down this path of figuring out how to help reducing latency will be tremendously valuable. And I think finally on top of that is these all awesome infrastructure, but at the end of the day, how to make it easy to use. It's all about good example solutions. I saw a lot of good blocks, but continue on providing these commonly challenging DNN solutions, examples and such. I think that would be very helpful for the community.
All right, now to you, Chitao.
Yeah, +1 to what Hing said about inference latency for the large language models. We want to see these large models being served faster and also supporting more higher throughput. I think it ties to the next topic, which is efficiency and the cost. I think efficiency is important because the global chip shortage means we may not get enough chips to run every single thing with the way the developer wants to run it 24/7. We want to maximize the efficiency we get from our hardware, the hardware fleet we can acquire from our on-prem and whatever cloud provider we can work with. It also means we want to control the cost. If machine learning is not done right, it can be very expensive. We want to making sure the cost here is under control and it's justified with the business growth and the impact the machine learning use case are created. That is why using more primitives from Ray to increase our machine learning efficiency and the reduced cost is going to be what we are really looking for next year.
Great. So I think the key points I heard: performance, cost, developer productivity. Yeah, Ray team will definitely keep note and keep improving Ray in the upcoming year. And yes, thank you so much for the great insights. Thank you for the great panel and the great start of day 2. Please enjoy your lunch, enjoy the afternoon sessions, and meet the Ray team at the Ray ground.